You ever see one of those massive container ships or a cruise liner just sitting at the dock? It looks pretty simple, right? Just a few really thick ropes holding it in place. But what you're actually looking at is an amazing feat of engineering, one that's designed to fight a constant, totally invisible battle.
I mean, just stop and think about that for a second. We're not talking about parallel parking your car here. This is like docking a skyscraper that floats, and then trying to keep it perfectly still while the planet is doing everything it can to move it. The answer isn't just get some strong ropes. Oh no, it is way, way more clever than that.
So what we see from the shore, it looks like this kind of carefully choreographed dance, right? You've got the tugboats nudging the giant ship into place, then the lines start getting passed over to the dock. First up are the spring lines. Those are the ones that run diagonally to stop the ship from surging forward or backward. Then come the breast lines, which run straight across to keep it from drifting sideways. And finally, the head and stern lines lock the front end back in place. Looks pretty straightforward.
But that whole physical process, that's just the tip of the iceberg. Because the second those lines are tied, the real work actually begins. That ship is now locked in a constant tug of war with some of the most powerful forces in nature.
Okay, so this is where we get into the real battle. And you have to understand, that word parked is totally misleading. A moored ship is anything but still. It's under a constant, relentless assault from the environment around it.
So what are we talking about? Well, first, there's the wind. A massive ship has the surface area of a building, and the wind is just slamming against it with incredible force. At the exact same time, under the water, the current is pushing and pulling on the hull. Together, these two forces create these enormous pressures, trying to rip the ship right off the dock, both sideways and lengthwise.
So you can see why you can't just, guess how many ropes you're going to need. Naval architects use some really sophisticated software to calculate all these forces with pinpoint precision. They design a very specific mooring pattern for that ship in that port for those exact conditions. And just think about all the data they have to crunch for this to work. They need the ship's exact size, its shape, how much of it is exposed to the wind. They need the projected wind speed, the speed of the current, the depth of the water, and even the precise angle and the material strength of every single rope being used. It's an unbelievably complex equation.
And the whole point of all this complicated math is to figure out the exact tension on each individual line. Why? To make sure the whole system can handle forces way, way bigger than what it's ever expected to face. It's all about building in this huge factor of safety. But that idea leads to something even bigger. See, all those calculations, they lead to a really important shift in thinking. This isn't just about having a bunch of individual super strong ropes and winches. It's about designing one single cohesive system where every single part is sized in relation to one core number. And that core number has a name. It's called the Ship Design Minimum Breaking Load, or SDMBL for short. You can think of it as the ultimate strength value for the entire mooring system. Everything else, every winch, every rope, every piece of hardware, is designed and chosen based on this one absolutely critical number. And this table just lays it out perfectly. It really shows you that system's approach. The winch's safe working load, it's set to exactly 100% of that SDMBL. The main mooring line itself, that's designed to break at just a little over that, 100 to 105%. And then, check this out. The mooring tail, which is a shorter, more elastic piece that absorbs shock, is even stronger at 125 to 130%. Every single piece is calibrated. It's like a symphony of strength. So what we have here is this perfectly balanced system engineered for just immense strength. But hidden inside this design is a secret. It's a really beautiful, totally counterintuitive piece of engineering that is the absolute key to keeping everyone safe.
This is where the real genius comes in. Because to make a system this powerful truly safe, you have to intentionally design a weak point. I know, it sounds completely crazy, but it is absolutely brilliant engineering.
So let me ask you, in a system where every rope can hold hundreds of tons of force, where every piece of steel is massively over-engineered, what do you think is deliberately, and I mean deliberately, designed to be the weakest link? The answer? It's the brake on the winch that holds the mooring line. It is the single weakest point in the entire system. And yes, it is that way completely on purpose. This is not an oversight. This is the most critical safety feature of the whole setup.
And here is the magic number that makes it all work. That winch brake is specifically set to slip The technical term is render, when the tension on the line hits just 60% of the system's total design strength. Not 100, not 90, just 60.
So, let's play this out. Imagine a sudden, monster gust of wind slams into the ship. The tension on one of those lines skyrockets, and it goes past that 60% threshold. Instead of that rope straining and getting closer to its breaking point, the winch brake automatically slips, paying out just enough line to release that sudden, dangerous spike in pressure. It's the system's emergency safety valve.
Because when you really think about it, the alternative is absolutely terrifying. The last thing you ever want is a multi-ton rope under that much tension to snap. The energy that gets released is equivalent to an explosion. It is far, far safer to have a brake that is designed to give way in a nice controlled manner long before anything gets close to its breaking point.
And hey, don't just take my word for it. This quote from Wilhelmsen Ship Service just sums it all up perfectly. The brake is designed to be the first thing to give. It is the sacrificial part that protects the entire system, and more importantly, it protects the people working on the dock and on that ship.
So the next time you're near a port and you see one of these floating giants tied to the dock, I really hope you see it differently. You're not just looking at some ropes. You are looking at a complex, dynamic system of balanced forces, a system that was designed with an intentional weak point that makes it brilliantly and so counterintuitively safe.